Hello, everyone, and welcome to this 23rd Urban AI conversation. We are going to start in a few seconds, actually. In the meantime, feel free to let us know in the comments who you are, where you are based, and what you are doing. Feel free also to connect with each other, to let us know also if you are on LinkedIn or on YouTube. It's also a way of connecting. And for us, it's a way of knowing if the live is working well on both of the platforms. So maybe a few words actually about Urban AI before starting and launching this conversation with Valerie and Daphne. So Urban AI is a global organization dedicated to the emerging field of urban artificial intelligence. We federate a community, a growing community of 200 international experts, to which actually Daphne is part. We also have a think tank with which we are doing research, experiment, and also event in the field of urban artificial intelligence. And lastly, we have an academy with which we are doing capacity building programs to help organizations, specifically urban organizations, in their urban AI journey. And as part of our work and projects on urban AI, we regularly organize urban AI conversations such as this one, during which international experts, public servants, and members of the community can present, discuss their latest project or research. And for this 33rd Urban AI conversation, we have really the great pleasure of welcoming Valerie Pascareia, a special data scientist at Google, and Daphne Tapia. You might know actually Daphne Tapia, or her face might be familiar because she was also the host of the 23rd Urban AI conversation dedicated to AI and remote sensing for urban sustainability. She's also director of business development at Emisight and Urban AI member, and we might actually also being joined later by another Urban AI member. This is a kind of last minute surprise. For this conversation, we will discuss and explore AlphaEarth foundations. We saw a lot of news, a lot of discussion on this topic, so it will be the time to explore it further. We will first have a 20-minute presentation by Valerie to explore further this topic, and then we will have a 35 minutes, 40 minutes discussion, collective discussion with Valerie and Daphne. And if you have comments, if you have reactions, anything, please feel free to share them in the chat, because we will also react on your comments and reactions during the live session. Valerie, the floor is now all yours for the presentation.
Awesome, thank you. Let me get my slide shared. So I'm Valerie. I'm very excited to be here today to talk to all of you about AlphaEarth Foundations and the satellite embedding data set, which sounds like you've all heard a lot about already. So for those of you who may not know, we've entered what we might consider the golden age of not just Earth observation, but Earth observation data archives. I work as part of the Google Earth Engine team, and in the Earth Engine catalog, we have just 31 million Sentinel-2 images alone, with millions of images from Sentinel-1, Landsats 8 and 9, not even including the full Landsat legacy, and literally thousands of other geospatial data sets. And it's not just what we currently hold, it's what we continue to add. For example, we add about 100,000 Sentinel-2 images every week. And as the graph on the right here is showing, we expect these trends to continue, where we're seeing not just more sensors, but also more images from those sensors, and this volume of data just continues to grow. And so we've seen a shift over the years from historically the challenge being having images to analyze in the first place. Now we have so much imagery that the bottleneck is really becoming the ability to process that imagery and build models on top of it to get to what we actually want, which are insights about our planet, whether that be land cover mapping, commodity mapping, water resource detection and monitoring, crop mapping, or urban applications. So we're really trying to do is figure out how to get people from imagery to insights faster and with less pain in that pre-processing of these massive archives and running models on top of them. which is why we are so excited to be announcing AlphaEarth Foundations and the satellite embedding data set, which I'll talk more about in a bit. But AlphaEarth Foundations is taking that idea that we have all these different views of our planet, satellites continuously orbiting, collecting data. It's almost like an image or a video that you can run where you're flipping through all of these different images like we just saw in this GIF. And what the model is doing is taking all of those images and putting them into a compressed representation, a feature space that you can then use for those downstream applications and modeling tasks without all of the standard pre-processing and other image harmonization, summarization that you might be doing. So again, we've got all these different looks of the planet from all these different sensors, and we built a model that's able to combine all of that and extract this more useful embedding signal from it. For those of you who have looked at our paper and are interested in the more technical details here, this is the overview of the model, at least like the conceptual high-level overview. You can think of it as a kind of standard encoder decoder structure here, where we've got raw image sources coming in on the left. This is a time series, so we actually have, like I said, kind of a movie of images from Sentinel-2. It's an optical sensor, Landsats 8 and 9, another optical sensor, but also thermal information and a panchromatic band, and Sentinel-1 radar data that comes in through a bunch of processing. We use what we call our space-time precision architecture, these STP blocks, which combine information from both the scene level, so like broad spatial context, temporal trajectories, so how the time series of values or observations evolves through time, and then our precision, which gives us that kind of per pixel detail, so using some small convolutions to preserve that spatial precision in addition to broader spatial context. I'll also call out, there's a block labeled summarizer here. One of the unique capabilities of AlphaEarth Foundations is it's not just able to produce an embedding or a representation per image. What we actually do is summarize over a specified period. Here it's labeled valid period, but we more or less give the model a time start and time end, and we're able to summarize the embedding results, the featurization results over that period. So once you've gone through the summarizer, you've got a 64D representation that is encoding, again, measurement context from our input sensors, as well as learned information from some targets that I'll talk about in a second. But we've got that measurement context, we've got spatial context, we've got spatial precision, and we've got temporal context, all packed into 64 dimensions. That's kind of how we get to the embedding piece of it. But if you're curious about how the model actually learns, that's the right side of the diagram where we see the reconstruction tasks. And so once the model generates an embedding, its goal is then to use that embedding to reproduce different images. And this includes images from our input sources, so Sentinel-1, Sentinel-2, and Landsat, as well as a bunch of other sensors that I'll show you in a second. But the model's job here is to take that embedding and decode it into various image frames using metadata from the individual sensors, as well as some other constraints. So we've got a bottleneck here that helps us structure the embedding space and some other objectives that really make sure that the structure of the feature space is as useful as possible for these sorts of applications that that remote sensing scientists and those working with Earth observation data typically pursue. And so if you're wondering, what are those targets? What are the other sensors you're learning from? Here is our full list. So in the table on the left, you'll see we've got the inputs that I just talked about, as well as a long list of targets that include everything from ALOS pulsar, L-band SAR, elevation from the Copernicus DEM, LiDAR observations from JEDI, climate variables from ERA5 land, gravity field data from GRACE, which helps us get at water and kind of subsurface dynamics. We've got some weak supervision coming from land cover information in the National Land Cover Database, as well as in our most recent update, the USDA cropland data layers, so some agricultural land cover information, and we've got text information, which allows us, again, to help structure that feature space and encode a bit of semantic information. And we sample these data sources across 5 million sites in our pre-training data set. So this is really globally representative. And it's not just the locations, we also sample multiple time periods, which gives us a total of about 10 million video clips that the model is being trained on. So it's able to encode this multi-source, multi-temporal information with a global sample of these video clips. And those clips in total have about 3 billion individual images. The chips are about 1.28 by 1.28 kilometers in size. So this is a lot of data that's being used to pre-train the embedding model. And really the result of this, if you take away one thing about how to think about AlphaEarth foundations, is we like to refer to it as a virtual satellite that can image any place over any time. And so if you look at that top figure here, those are individual image sources. We've got these, sporadic observations. They're non-uniformly sampled. They exist in separate archives, separate data streams. And what AlphaEarth Foundations is doing is harmonizing across all of those different sources and giving you the ability not just to look at a single snapshot or a single point in time, but really to summarize the information over a continuous period in order to better represent the conditions for that period. And so the output of the model is what we call an embedding field, getting at that idea that we have a representation or an embedding vector for every 10-meter pixel on Earth's terrestrial land surface and nearshore waters. Each of these embeddings, as I said before, have 64 dimensions. And so these are 64 learned axes that represent all of those spatial measurement and temporal contexts for each location on Earth. And we're surfacing these as a data set to make things more useful for our users. I'll talk about that in a little bit. But before I get into the application side of it, I want to take a quick detour and tell you a little bit more about how we evaluate these representations, because you can imagine it's really tricky here. We're learning a representation. There's, unlike a physical measurement or a band from, say, Sentinel-2 or Sentinel-1, where we're actually capturing a reflectance signal, there's something physical that we're measuring. These representations are learned. And so they're coming out of the model, and there's really no source of truth to compare them to. Rather, we use proxy tasks or evaluations that represent things that we would hope people to do with the embeddings in order to characterize our performance. And for our model evaluations and what's presented in our publication, we did a massive search of existing reference data sets, high quality label information, and other publicly available data sources, and ultimately ended up with a set of 10 different sources from which we derived 15 different data sets. You can see for some of the sources, we may have used multiple labels or combinations of variables. And all of these were designed to represent what we consider real world applications of this data. These aren't just academic benchmarks. These are point-based data sets that represent how people make maps today and production use cases for remote sensing observations. And we cover a mix of different domains. So land cover mapping, crop type mapping, plantation mapping, evapotranspiration, emissivity, all sorts of different types of data. And we also look at not just classification problems, so assigning individual labels to periods of time, but also regression problems, so continuous variables, and change detection, so being able to characterize changes in the state of land through time. And we have a mix of temporal cadences as well. So remember I said we can summarize any period, and so our evaluations included a mix of annual labels in the case of a lot of land cover and land use type applications, as well as some single date measurements and monthly aggregations in the case of evapotranspiration. And across all of these, one thing I'd like to highlight is that max trial size column. And so what we do is we take for each of these data sets, we've got a train and a test split, and we're using very simple classifiers. So this isn't super powered AI as much as it's just basic classic ML. We use KNN and linear classifiers for our trials. And when we're training those classifiers, the maximum number of points that we use in our evaluation pipeline is 300 per class. And so imagine you only have 300 labels, which is a relatively small size compared to most kind of modern Earth observation machine learning that could take, thousands, tens of thousands. We've seen billion pixel data sets. And so these are relatively small, reasonably sized training sets. And we're looking at our performance, not just on any one of these data sets, but across all of them. And I'd also like to point out, in order to kind of set the bar for how well we're performing relative to existing approaches, we do consider AlphaEarth Foundations a featureization approach. And so we compared to other ways that people might featureize the landscape. So we had a set of controls where we looked at just spatial coordinates and elevation information. So how well can you predict, say, land cover if you are just giving a model the location on the surface of the Earth? We tried a vision transformer as a control on, do you really need something that's specific to Earth observation images, or can you use a vision transformer that's just pre-trained on standard camera images? A bunch of kind of standard remote sensing feature approaches. So composites, when you take a bunch of images and take a mean or a median over individual bands to build your feature vector. CCDC, which is a harmonic fitting approach that takes into account temporal context when engineering these features. Mosaics, which is a designed feature space that uses kernels to learn an embedding, as well as a few different Earth observation specific foundation models, including SetClip, which is an implicit model for Earth observation data, and Prithvi and Clay, which are some well-known Earth observation foundation models. And all of these we compared using the same evaluation set that we used for AlphaEarth Foundations. And another thing I'd like to call out in this table is the dimensionality here. So as I said before, AlphaEarth Foundations produces a 64-dimensional embedding. This is actually relatively small as far as embedding approaches and kind of large foundation models go. Those can typically have 256, 768, 1024 dimensions to the output embeddings. We're very much thinking about practitioners here. So you'll see with things like composites and CCDC, we get much lower dimensionalities. And so we ended up going with 64 as a trade-off between kind of the representativeness of the space and the ability to use it for standard ML applications in platforms like Earth Engine and other geospatial analysis workflows that typically work in, use feature vectors, but not necessarily as high dimensionality as you might get from these other approaches. And the big take home here was that AlphaEarth Foundations was able to improve error magnitudes about 24% on average. You see our chart here where you're looking at the rate of error improvement. These are kappa adjusted. Balanced accuracies, so as conservative as possible, making sure we're looking at ourselves relative to the next best model, which is listed on each of the bars. And really the big take home is that we were able to achieve higher performance on all of these benchmarks, not just any single one, but really the full suite of tasks. And that's how we think about performance, in that, we're able to achieve good scores on the sorts of applications that we would expect users to be pursuing, and that we're able to perform consistently well across all of those relative to other things that would be available today. That said, as I think everyone knows, it's not just about how you perform on these sorts of benchmarks in these statistical comparisons, but really how the data set, how the model results perform in realistic user workflows. And that is part of why we launched the satellite embedding data set in Earth Engine. And so the satellite embedding data set is our newest collection in the Earth Engine data catalog. This is a collection of annual embeddings, annual summaries generated by AlphaEarth Foundations. There is a embedding layer for every year from 2017 to 2024. And these, for each pixel, we have an image where there's a 10-meter pixel resolution and a 64-dimensional feature vector for each of those pixels. And you can use this just like you would use any other satellite image inputs for classification, regression, change detection workflows, and some other interesting things like similarity searches. So just to call back to the diagram I showed earlier, this is us actually taking the model and running it at scale, using those those various input sensors to get to a 64-dimensional embedding for each of those pixels. So we're doing all the inference, we're running the model, the data pipeline, and we're surfacing this data set to make sure that it's useful and usable to practitioners who really want to get to those insights and those end stage applications. And I wanted to, in closing, give us a really quick tour of just some applications that we've seen or explored ourselves that I think would be relevant for your urban scientist community. In particular, we've got this GIF on the right here is actually showing just in the raw embedding space, so picking 3 of the 64 embedding axes and tracking them as an RGB image. We can see this is a development in Florida where they're constructing new housing, new roads, and major changes in the landscape over the time series of the embedding data set. And if you can see it in images, you can certainly train classifiers and other algorithms to start to classify those changes and attribute them. Because we can capture all of this spatial and spectral and temporal context, the embeddings are really powerful for identifying things like just general patterns and typologies in urban landscapes. We've seen some cool clustering examples where you can get at different neighborhoods, neighborhoods that have more tree cover versus less, or different building arrangements and structures. And so you can start to use the embeddings to classify, cluster, that sort of thing. We've definitely seen some maps of urban land use and impervious surface cover, and I'll show you a couple of those just from our own tests in a sec. And we see a lot of applications just being able to scale incomplete measurement records or sparse measurement records. So for example, imagine you have a data set of buildings where you only have a type for some of them. You could, in theory, use the embeddings to help you build a classifier to use your existing labels and label unseen examples. You do that with buildings, tree records, all sorts of interesting ground level data. And that's really what embeddings are most powerful for, finding things that are similar, clustering like with like, and scaling measurements where you have kind of an incomplete or sparse representation of the information you'd like to scale, and being able to make an entire wall-to-wall map of that. And so just to, again, show you quick examples, this is a demo of similarity search. So really just taking the dot product or the angle between embedding vectors for a selected example and all other pixels in the data set. Here we're seeing a pixel for downtown Manhattan. And so you're looking at very tall buildings, skyscrapers, and what you see in the maps is the similarity between that example, which is the little square down in the corner, and globally some other cities. So what's lighting up in the brighter colors here are places that are most similar to the sampled location. And we can see in San Francisco, London, Buenos Aires, Tokyo, that we're picking up on similar high density urban areas as most similar in embedding space, while things like vegetation and water are showing up in that less similar, darker side. And if you go to the link here, goo.gle/satellite embedding similarity demo, you can try this for yourself, click any location, and almost instantly start to make a similarity map for the rest of the world. I did mention on our evals that we do work on land cover as well. So here's New York again. I am New York based, so tend to have a lot of examples here. But if we just look really quickly at a couple of data sets that capture urban land cover types, so LCMAP and Glance are two reference data sets that we used. Both of them have a land cover classification. And if we look at not necessarily just our low shot information, but here's a random forest trained on the 300 points per class from the LCMAP data set. The red here is an impervious class, and you can start to see with just 300 examples per class and a really basic random forest, we're able to start making a pretty good map of the distribution of impervious surface in Manhattan in the Northeast. And you imagine if you zoom out even beyond, just to show you another result from the evaluations, here's the performance relative to the models I mentioned earlier, other featurization approaches. And you can see AlphaEarth Foundations is topping out at over 80% balanced accuracy on this classification, which is above all of the other results. And if you end up throwing even more points at it, because if you have data, why not use it? We can even refine that map of impervious surface even further. So if I flash in between by adding more labels, we're getting a higher quality result And you can start to quickly make these sort of maps. I'll go through really quickly here, but same sort of setup with the glance data set. Here, the legend is a little more detailed. We have a class called developed instead of impervious. But if we try with just our 300 points per class and a simple random forest, we get a map that, again, captures those broad scale patterns. If we look at our low shot comparisons, we're again performing really well on this task, even just using those simple KNN and linear classifiers instead of the random forest. And if we go all the way through and start adding more labels per class, the kind of the full data set here without using the evaluation split, we'll see a refinement in those patterns. Central Park here looking really good with, you can see the pond in the middle, pathways in between, some of the grassy areas versus tree cover. So both the level of detail and that kind of broad patterns. Finally, if we take Glance, which is a global data set, and zoom on the other side of the world to Singapore here, just to prove to you it's not just US examples, we can use information from anywhere. And if you're training kind of a global pre-training data set, a global data set here, you're able to map anywhere in the world with your labels. And so really rapid tour, I want to get to the questions, but in summary, just take homes, AlphaEarth was designed to function as a sort of virtual satellite where we can summarize surface dynamics over space and time. And we're able to learn these patterns across all of the data streams that I mentioned earlier, and in the process generate both a spatially and temporally precise embedding vector, meaning it's 10-meter resolution, and we have an exact constraint on the time period that embedding represents, and we can do this globally. I didn't get too much into it, but again, our outputs were really designed for practitioners. If you've ever worked with an image composite, you can think of this as a very fancy AI-powered image composite that you can plug into any existing Earth observation workflow. You might use Sentinel-2 or Landsat or Sentinel-1 for. And we think of embedding images as this new foundation on which many, many different Earth observation applications can be built. And we're really excited to see what the urban community is going to do with them. And I have some slides here I can leave up for a second. If you want to learn more, we've got lots of blog posts. Our paper is out on archive. We've got the data set available in Earth Engine, some tutorials in our Earth Engine developer site materials, and you can read more about embedding vectors in general if you're curious. And with that, I will stop my share. And
Thank you. Thanks a lot, really, Valerie, for presenting definitely this fascinating research, even kind of mind-blowing research. Actually, a lot of questions, I think, and we will discuss it now during the following 30 minutes. Maybe, so just before, again, I see already some comments pop up. Please keep sharing your questions, remark, and we will definitely share them during this conversation. Maybe the first question is more an observation. So you share, in a sense, all the richness of those data sets. And this richness, in a sense, is also made possible because it's primarily for AI that all those information are compressed. So I'm wondering, is it the first time that such geodata are primarily compressed, created for AI analysis? And what signal does it send, in a sense? Like, why did you have this idea of creating those embeddings for AI?
Yeah, so we compared with a lot of other featureization approaches. So I would say it's certainly not new to want to compress and featureize Earth observation imagery. Historically, this has been done more in the sense of designed features. So think just spectral indices are a way of compressing and representing information from Earth observation, NDVI and DSI, those sorts of things. In terms of featureization, we've seen a lot on composites, on the harmonic type features. So again, those are people bringing kind of a pre-existing structure and their own knowledge of these signals to featureization. We've, in more recent years, seen this explosion of geo foundation models and these larger deep learning models designed specifically for Earth observation. And so there's definitely been a push around that more generally. I wouldn't say we are the first, but what we really were trying to do was fill some of the gaps on being able to synthesize through time. So being able to account for not just the measurement context or being able to generate kind of a per image embedding, but really to provide those summarization capabilities and perform compression in a way that you had a well-structured embedding space. And so it's not just kind of putting all the data in and getting a representation out. It was intentionally designing an embedding space. And that's why we think of AlphaEarth Foundations as an embedding model, as opposed to kind of a more general geo foundation model, because it really was designed to make high quality embeddings.
Okay, super interesting. So there is indeed like this idea of making it practical. So thinking like for end user, and we will discuss it again to see like what are the possible applications in the urban field. While preparing this episode, I saw some reaction comments saying in a sense that those embeddings are black boxes. Could you maybe explain, Valerie, why could we say that those embeddings are black boxes, and what does it involve?
Yeah, so when I hear people refer to black box, I think about the fact that they're learned. So the model is able to determine how to structure the axes, the values that it's assigning. So a lot of the remote sensing community, we're so used to working with images where our bands represent physical measurements. So when we say red or near infrared or HH polarization, it means something in the physical world. It has a value that represents a measurement. When we're dealing with these representations, it's more like a principal components analysis, where we're allowing a model or something driven by the data to find the representations, the interesting axes. And so in one sense, we end up with something that is less directly human interpretable. I can't necessarily look at the embeddings and say, here's the Sentinel-2 component, or here's the vegetation component. But what we're sacrificing in that explainability, we're getting a lot more power and allowing the huge capacity of this model to learn from the data directly and be able to give us more powerful representations, even if they aren't as directly physically interpretable as kind of these individual axes or channels.
The fact that they are not directly, let's say, human interpretable, does it involve that, for example, we might need some third-party verification? So, Daphne, as you are also in this GeoAI ecosystem as a possible user of AlphaEarth Foundation, what do you think? Would you like make some third-party verification, or would you trust as it is such embeddings?
It's a bit hard to say. What we can say for sure is that when you have raw imagery, it's very easy to do visual inspection. You can see a forest, a fire, anything. And as you said, Valerie, embeddings, it's not interpretable for human beings, really. So there is a need for clear documentation for sure, and maybe Google is working on it. But I think my concern would be more about reproducibility. Let's say if tomorrow you decide to change the AI model for some reason, how do we do to have a consistent work with what we did in the past? I have another question, for instance, about ground truth. You showed on the example a lot of forest, urban, etc. But is there any ground truth benchmarking? And and finally, maybe third parties could be interesting to set for certification. But I guess maybe that would come from the governments that could write rules or suggestions, etc. But it's open.
Yeah, I can speak a bit to the evaluation. So really, I showed our set of benchmarks. So those are data sets that we curated, we rigorously structured so that we have train and test sets. There's separation between the points, we balanced labels, we generated a lot of statistics. So we did our own evaluation in the lens of what would people be doing with these embeddings. It's really hard to evaluate, again, the embeddings directly, but we're looking to these proxy tasks. And we didn't stop there. We had a huge trusted testing program where we had a lot of different organizations, different use cases, folks contributing their own evaluations to our just understanding of the embedding space. And so we did very much look to external parties to vet whether these were working for real use cases. And now that the data set is out there in the world, we're already seeing publications. We're seeing, we just had our user conference for our Earth Engine and geospatial community at Google just about 2 weeks ago, and seeing lots of new and exciting applications. So really, when I think about third party, I'm thinking about people using the data in the wild and what they're getting from it, and their own evaluations and what they're publishing will help guide, you know, the future of understanding what's captured in the embedding spaces. And I also want to make a quick note on reproducibility. That was a big reason for generating the satellite embedding data set and taking this model as data set approach. So as you're alluding to, like anytime you change a model, rerun a model, change its inputs, you can get some variability. We expect the model to be generally stable. We've done a lot of work to make sure that we're not sensitive to dropping different inputs. We ran a lot of ablations to test model sensitivities on different axes, but really we wanted to have a version of the embeddings that people could build on and be able to reproduce and share information around. So the data set is a full model run. It is using a consistent version of the model. When we add new years to that data set, it will continue to be the same version of the model going forward. And if there were a change in the model, we'd change versioning on the data set as well. So we definitely had an eye towards reproducibility, especially when you're dealing in these big modeling spaces. Having a data set kind of locks in a version and allows you to reproduce others' results and really, like, again, share that same foundation for anything you're building on top.
That's super interesting, because we see that you are actually building an entire ecosystem. Either it is like for explainability, or let's say third-party checking, or either it is for application. Like those embeddings, AlphaEarth foundations, like they are allowing like new applications and new ecosystem to emerge. I see multiple comments actually regarding like urban applications, like especially, for example, one comment from Gerardo Ezequiel Martin Carreño. I hope I pronounced all your names well, Gerardo. Beyond finding similar urban patterns, can AlphaEarth help us understand the why behind urban challenge, like what drives urban height island formation, and predict future thermal vulnerabilities with reasoning we can validate? So super interesting question, and maybe it makes a great transition for like the second part of the discussion, which is more dedicated like for the AI implications. So we said it a bit with Daphne, with you, Valerie, that those embedded, they are designed for AI utilizations. And like one of the, let's say, use of AI, of urban AI today is also through LLM. And they really had a kind of rise of AI research through LLM. The thing is that those LLM, they are not very good at reasoning with spatial data. Like those data, they are very different, let's say, from textual data or other data. And actually, we're lucky enough today to have Alexander. Alexander, are you here? Hopefully you're here, Alexander. Yes, amazing. Hi, Alex.
Yeah.
So we have, great to see you, Alex. So we have Alex from Aino World. Maybe Alex, you can present what is doing Aino World, and could you explain us why LLM are not that good at let's say analyzing spatial data, and what needs to be done to fix this in a sense?
Yeah, thank you very much. That's because LLM is not is solving different tasks actually. So it's not about the data generating, and the only thing that you can trust large language model is actually to retrieve and somehow aggregate, analyze data that already existed. And the biggest challenge so AINA is a tool that help not technical users. Not technical at all, not technical users, like architects, urban planners, policymakers, to retrieve and analyze geospatial data easily. And the biggest problem that we faced while working on our products is actually lack of data. So, and that's why I'm pretty happy that such fundamental model existed. And it's really fundamental model because it changed everything. And the biggest challenge that we face in our product as a delivery based, like a knowledge-based product, is actually lack of data for the not developed for developing countries and developing cities, regions. And for instance, we have a lot of users, thousands of users from India or Saudi Arabia, for instance, and we cannot support them. We cannot help them. Okay, a large language model is amazing in data management and data aggregating, but if you don't have any data, sorry, you cannot help your users to solve their problems. And that's why I really happy that such models appears. And 5 years ago, I cannot even imagine that somehow it's possible to embed the whole planet. Now it's possible, but for end users, for like not data scientists but for architects, it does not solve their problems yet, because they have to get well labeled data they can trust. So they would like to see, okay, there is a building, there is a road, there's a building with 10 levels, and there is the coverage of this road is like this, whatever. So they need a really well vectorized, well labeled data they can use for their data analysis, because anyway they're gonna export it for the Adobe Illustrator, for their presentations, and all consultancy still working the same way, in this way. So that's why there should be some kind of proxy between the fundamental models and the end users. And I know that in your strategy, Valerie, you already allow platforms to use your API to use it for the data pipeline. So am I right?
Yes. You can absolutely build in the Earth Engine pipeline into any other larger workflows. And we are also, I should say, looking into options for surfacing the collection outside of Earth Engine. So think like on regular GCS, if that's been a blocker for anyone on the line, we are actively working on getting our copy available outside of just the standard Earth Engine collection format. So hopefully that opens up a lot of new opportunities. Yeah,
and for me, it sounds like a pretty amazing that if you have any ideas that you can somehow build a partnership with a crowdsourcing company, organization like OpenStreetMap, that would help you to validate data and label it and deliver it to the end users, maybe that would be pretty awesome. I know that Microsoft actually labeled buildings footprints almost all around the globe, and that helps a lot. It helps a lot for global South countries and areas.
Alex, so, if I may ask, like, because with ANO, so you said it, like, to manipulate GIS data through request in natural language. So really, I encourage you, by the way, to have a look at what they are doing. That's really amazing. So, like, concretely, like a solution like AlphaEarth Foundation, as Valerie presented it, you said it might allow you to have a more geographical scope. Does it? Exactly. So more like geographical coverage. Does it allow you also to have access to new urban analysis, urban potentially?
Yeah, exactly. And that such kind of models just deliver the new value for users who definitely don't have any data. And that's unreal to imagine that someone will label their areas manually. So we can rely on AI and like basically object segmentation via satellite images to make a better coverage.
And are they usable as they are, those embeddings for you with, let's say, your LLM, Alex, or do you need to do extra work to fine-tune the LLM to work with the spatial data, just to be a bit concrete for like maybe urban planners, data scientists looking?
Yeah, actually, we are trying to solve a pretty simple task. So users might ask the question in natural language about the area they're interested in, and what do we want to analyze using such data. And that's our goal, is to predict what data source and what specifically data provider and data basically is better to reply users' request, and how we can aggregate it for them. So, but if there is no data, it's better to show users that, okay, sorry, there is no data for this area. Zero found it. We found it zero object, rather than hallucinate and design something that it doesn't exist at all. So, and that's the main difference between the general language models that you can try for data analysis and something that we are trying to build. So, okay. And our goal, our strategy actually is to increase and add more and more data providers that we trust, that we can use for data aggregation and data analysis.
Okay, so typically you would integrate like AlphaEarth Foundation into your workflow, into
That would be amazing. That will be amazing. That's a part of our roadmap. Not now, but yeah, definitely.
Maybe another question on the AI part, actually, and it's also resonating with some of the comments. We hear, like, I read like several people saying that the added value will be on the ability of AI to reason, to make sense, or at least to create some information based on those embeddings. It is sometimes called physical AI, this ability, this property of AI to reason on physical properties. For whoever of you wants to answer this question, what is physical AI concretely, and why it is a change maker for like analyzing those embeddings?
I have no idea what physical AI is, to be honest. So that's something new that just appeared, and I discussed with some companies who are in this field. And basically, that means that they aggregate data from many kind of unmatched data sources and into one data pipeline that might be image recognition, satellite image analysis, vector data analysis, sensors, and so on. And so combination of this is like as we call it now, like a physical AI. But it's something pretty new. I don't really know how far that might go.
Okay, then we will. Oh, yeah, go ahead, Valerie.
Oh, I was going to say, so in the AlphaEarth Foundation's work, we focused a lot on even more just like classical ML. So like I mentioned, like we are designing a feature space that we hope works well with, you know, a KNN classifier where you're looking for things that are close together in the feature space, or just simple linear classifiers, tree-based classifiers. And so kind of lowering the barrier on the models side of it. So if you're building on top of a feature space that was generated by this very large model and a lot of data sets to begin with, then hopefully you can use smaller models on top. That said, there's all sorts of opportunities. Like we've talked a lot about map making because that was the community we were kind of building with in mind, but we've already seen some really cool applications. Again, I mentioned we had our user summit and we saw some folks who generated, I believe it was like average of embeddings over patches that they had labels for, and they were able to train a VLM, a visual language model, to then just open vocabulary query other patches based on what they had learned from that initial labeled data set. So to your point, Alex, it always requires some sort of labels. What we're really providing is a new modality in terms of vectors. We have text embeddings, we have image embeddings to do like regular camera image search. Think of this as a way to do Earth observation, either image search or building on top of them like you would any sort of other source data set from the remote sensing side. And so I think there's a ton of opportunities to pair with other types of embeddings, other types of models, and really, again, it's just giving folks another way of processing Earth observation data and building it into those sorts of work streams and models.
Okay, so different typologies of AI can be applied: LLM, computer vision, physical AI. We will do an episode on this to understand exactly what it is. For very diverse applications, you just shared them, Valerie. Maybe regarding now the GeoAI ecosystem, so trying to understand like how AlphaEarth Foundation is fundamentally transforming the GeoAI ecosystem. Question for you, Daphne. Could you maybe explain us the traditional, let's say, satellite imagery ecosystem, and explain how AlphaEarth's embedding approach might challenge this model?
Yes, of course. So in the satellite imagery ecosystem, we need to start with the satellite imagery provider. We have free sources like NASA, Landsat, Sentinel, as you mentioned, but we also have commercial providers like Airbus, Maxar, and they are selling pixels and raw data. After that, you have the users. We are the users. You have governments, you have GIS companies, you have agri-tech companies, and actually they spend a lot of time and money pre-processing the data. And finally, you have the analytics company that build products on top of all that. And so far, the value chain is going from the pixel to the pre-processing to the application. And the business model very often is following a price per pixel or price per square kilometer. It depends also on the frequency and the resolution of the image. So AlphaEarth Foundation is really changing all that because it delivers embedding, no raw pixels, and it lowers the barrier for everyone that wishes to enter the market. So I would say that AlphaEarth, like it switches the focus. So everything is AI ready. It works with any kind of sensors, with API connection. So it's really challenging the model that was established so far.
But you say it lowers the barrier, but in a sense you also need AI. So like you might think that you also need more resources, more capacities. No, isn't there a kind of paradox between the fact that you have more data, more accessible, but that are only readable by AI?
I think we also, with how LLM entered in our lives so fast and everybody speaks about that all the time, it's only a matter of education. So maybe for now it's a bit new, it's a bit scary, but you need to take the train with everybody, I guess. What do you say, Valérie?
Yeah, and I would add, like, where AlphaEarth Foundations and the satellite embedding data set are designed to complement all of those existing data streams. Like, we cannot exist without the data streams that we are built on top of. And I like to think of it more as like a higher level processing, right? Like, we're used to having top of atmosphere versus surface reflectance, where we've processed to surface reflectance, or all sorts of algorithms that do feature extraction. And so we're just adding to that legacy of a higher order processing level that allows you to extract more value and kind of get straight to what you want to be doing with the data faster. But that doesn't mean there's not still a place for looking back at the high-res image sources or fusing between different image sources. You know, do you want to do an object detection on a single image and then use the 10-meter embeddings that are representing all of this other context to then, you know, aggregate a signal for that footprint and do some classification? So I see it as, again, like an advancing and a layering into the existing system and giving you more options for combining data streams. And again, like in terms of lowering the barrier, it's about you're going to spend less time trying to find and source data, apply your own corrections, and really get straight to what's of interest to you. One last flag I'll give, like, even in just looking at high-res ordering, you could imagine, you know, you could use the embeddings to look for change over time. Our example on the Earth Engine catalog page shows you how to use a dot product for a to-date comparison. Find the places that are most dynamic, and then, you know, look for your ordering to really hone in on changes, kind of getting at some of what's coming up in the chat attribution, that sort of thing. So again, just a new tool in the toolbox as opposed to a complete disruption or replacement of any of these incredibly valuable sources that we already have available to us.
You mentioned object detection, and I see with Sentinel and Landsat data, we speak between 3 meters to 10 meters spatial resolution. In my company, Misite, where we work, we specialize on high resolution imagery to detect objects at 30, 50 centimeter resolution. How do you see the future for that? Is it the reason why we will always need raw imagery for satellite high resolution acquisition, or in the future, do you plan to implement higher resolution into your workflow to focus on object analytics level?
We've definitely focused on more the moderate resolution, publicly available image sources. Again, like usually when I'm thinking about object detection, you're not getting that at the 10-meter resolution. That's definitely better suited for those high-res applications. And there are so many models out there already for doing object detection and kind of using that high-res image context. Building on what I said before, I think it's more of this complement. Like if you can do kind of coarse passes to begin with, even if you don't have labeled data worth calling out, you can run clustering, very simple unsupervised clustering, or those sort of similarity searches where you may be able to group areas of interest or things of similar type and kind of target your object detection. But really, we were looking to provide these kind of higher level landscape summaries to complement other types of imagery and other types of those high-res models, as opposed to something that we could directly do within the framework of what we're modeling right now.
We got some super interesting reactions in the chat. I'm displaying one here, one comment. Well, again, I hope I don't mispronounce your name, Ersan Rehman, who is saying the real value of AlphaEarth would not only be in identifying spatial correlations, but also in providing interpretable reasoning about why urban changes occur. So like the why again, not only the what's happening. For example, in the case of urban hate island, by the way, we discussed it with Daphne during 23rd Urban AI conversation. So feel free to have a look on this. In the case of urban hate island, it could help disentangle drivers such as land cover transformation, built density, material albedo, and vegetation loss. If the system can embed causal explanation and allow researchers to validate them against ground truth data, then it becomes more than, I think it might be, data. Valerie, do you want to react to this?
Yeah, and I would say this sounds like an amazing use case and research application. So I go back to, we surface the data set so that people could pursue exactly these sorts of things. We've had lots of users looking into change attribution. So not just kind of this unsupervised approach I was mentioning, where you're just looking at, did the embedding change year to year as a way of finding change, but really providing some sort of label, or again, ground truth data to label the types of change. We've seen this for kind of forest monitoring applications, drivers of forest change from some of our testers. But really, we were in the business of making the feature vectors, and we're really leaving it to the user community, as the existing modeling communities, the people who have that domain expertise, to build the workflows on top of it to answer these more causal questions. Like, y'all are the ones who have the amazing data and the on-the-ground knowledge that you can build those relationships. And hopefully, like to what Daphne was saying about lowering barriers, we've made it easier to kind of have the features you need to do that, but it's still going to require the data and kind of the application-specific modeling context on the domain side and the user side.
So Alex, with Inner World, like that's definitely for you, this this message. Maybe if possible, two last things I really would like to explore with you. One remark, one observation from Ali Ahmad Alipour. He actually had a super interesting newsletter. I think it's called Unpacked GeoAI, working also at Google, but he's not he's expressing his own opinion. And he said the geospatial data market is moving away from public good toward a competitive, commercially driven ecosystem. I think he said this actually when he was analyzing GeoAI, GeoLLM. Daphne, can you explain this? Like, why is this geospatial market moving away from public data towards like a more competitive private ecosystem?
Yeah, so as we know, and as Google is using at the moment, satellite Earth observation data used to be free. I think Landsat is free since 2008. Copernicus data have an open data policy as well. And I think they were considered as something for the good, for the people. And over the last decade, there was some private satellite companies like Airbus, Maxar that started to deliver maybe premium products with high resolution imagery, frequent revisit time. And some might say that it will increase asymmetries between free and paying data, but on the opposite, I think it really created a lot of opportunities for innovation. And again, I think on top of that AlphaEarth Foundation, there is a bit of ambiguity there as well, because on the one hand, it's free data, I think, for research and scientific purposes. Maybe it's paying data for commercial purposes. But in all cases, it's an opportunity for us. Even though maybe all the knowledge or the embedding will be concentrated for now within one big player, which is Google, so it might have some limits in the future, but it's it's an opportunity, I would say.
Yeah. I would just add that the layers are available by CC BY, so they were intended for free use in line with use of other big image archives. And yeah, Earth Engine has always been free for non-commercial use and research. And we're looking into opportunities, like I said earlier, about surfacing the data in other ways just to broaden that. So goal is definitely on accessibility and broad use here.
And maybe also to resonate with this in the future, let's say you Emisight or you Any World, how do you envision potentially integrating those data without unveiling, let's say, a secret strategic insight from your company? But what do you already have in mind, maybe?
I think AlphaEarth will help us because it's global, so it will answer the question well. So if we focus on change analysis, anomaly analysis, you know from afar where to focus. And maybe after that, we will acquire high resolution imagery on a specific location that we have highlighted thanks to AlphaEarth. And on top of that, produce object detection analysis. So I think this is the main application for us. Okay. But Valérie, I'm curious if you have any other suggestions. I'm taking them.
No, that's a great one. Yeah, and happy to continue conversations as you're exploring the data set and potential applications. I do think we're in a very open space where we're learning so much. People are coming up with all sorts of new applications. So yeah, we're also keeping our ears to the research world and the commercial world and seeing all the things people are trying, because we're learning new things about what people can do every day as well.
Alex, on your side, you shared it a bit, but maybe.
Yeah, I would like just to add that for me, that sounds like there is an essential stuff people will use for the very beginning for each project. So basically, if you work on an urban environment project, such kind of models and data that delivered with them, that's literally like a Google. You start your each work with Googling, and if you have such data sources that you can trust, your user experience will start with just looking through this and see how it's going in this area. I would like to add that from our perspective, we are focusing not on data scientists, not on researchers, but on people who don't really know how to code, but have to design cities. They used to work on the small areas. So, and our goal is actually not to deliver the whole data that's available, but to filter it right, to keep it small, and to keep it hyper-local. That's our goal. And if I have a chance to integrate such models today, I will definitely do it, but it takes some time for us. So that would be just a part of our roadmap. And I really hope that we will see more models. We will see more type of data and integrated data from your side, prepare data for different use cases. I don't know, human validated data, AI validated data that made by AI, many options. That sounds like a really, really huge market just appeared with such model. And yeah, that will be amazing to see how far we can go with it.
Growing and lot of opportunities,
Exactly.
definitely. Last question, and that will be actually our conclusion. Valerie, what are the next steps for AlphaEarth Foundations, if you can share it?
As I mentioned, we're super excited to keep seeing all the applications that folks are developing and like looking for publications and blog posts and all that great stuff. We are, like I said, moving into making the data set available more broadly. So thinking like into a cloud bucket so that it can be used outside of kind of just the Earth Engine catalog and workflows there. So hopefully broadening some use. And we're looking into the generation of custom time periods. So we started with an annual data set as we thought that would hit the broadest array of use cases. We see a lot of annual mapping, but if you're thinking I have something particular that I would need a finer scale, we are looking into options there and kind of in the early stages of development. If you're interested, we have an issue tracker through the Earth Engine data catalog. You can file a request saying, hey, I'd love to see monthly or weekly or something like that, and really trying to understand what users might need in that sub-annual space going forward.
Amazing. Well, thanks a lot, really, Valerie, Daphne, Alex, also for joining, for sharing all those fascinating, exciting, also insights. It's really quite exciting, actually, to be here right now and see all those opportunities, all those possible collaboration coming, especially for urban artificial intelligence. And so if you are an urban practitioner, or if you are maybe urban planner, data scientist, maybe play with those embeddings. And even us at Urban AI, especially us actually, will be interested in having your feedback on this topic. And it's also something we're already actually exploring. That's already the end of this Urban AI conversation dedicated to AlphaEarth Foundation. Thanks a lot to our amazing speakers, Valerie, Daphne, Alex, again. Our next Urban AI conversation will be next week, not on Wednesday. It will be on Friday, actually, September 19th. And we will ask and wonder if LLMs drain or multiply urban planners' attention. You see that we discussed a lot today, LLM. So are they actually draining attention, or are they really freeing attention of urban planners? This is a topic we will discuss with Jonathan Metzger. Thanks again, everyone. Thanks for joining, and take care.
Thank you very much.